Hello, let's talk about second partials in a function with several variables. Just like with a single variable calculus, there is a second derivative for these types of functions. In fact, there's going to be multiple second derivatives. If we take a function with two variables, each partial derivative can be differentiated. And that means we will end up with 4 second partial derivatives. The notation is a little bit cumbersome. You can see we've got the squared partials. We're not actually squaring anything, that's just notation that says that it's the second derivative. We can write it a little bit more succinctly as f subscript xx for the second derivative with respect to x twice. We call that a own second partial, and f subscript yy is the derivative of f with respect to y, and then the derivative of that again with respect to y. We also have these cross partials, and so we take the derivative of the function with respect to x and then take the derivative again with respect to y, or in the opposite order, and these are denoted as f subscript xy and f subscript yx. How do we interpret the second partials? Well, we can interpret them as changing marginal effects. So let's take a look at the own second partials. F subscript x is the marginal effect of x on f. So maybe that would be like the marginal change in cost, or the marginal change in output, which we call the marginal product. F subscript xx tells us how that marginal effect of x changes as x changes. If we look at the cross partials, f subscript xy tells us how the marginal effect of x changes as y increases. F subscript yx tells us how the marginal effect of y changes as x increases. And if the mixed second partials are continuous, then it turns out that the order we take these derivatives doesn't matter. And you're going to see many examples of this. Right? F subscript xy is just going to be equal to f subscript yx. So the order in which you take the derivatives doesn't matter for these second partials. Here we have an example, and the example says compute all second derivatives of the function f of x, y. The question asks us to compute all second derivatives, so why don't we give that a try? In order to compute the second derivative, a good place to start is by computing the first derivative. So we've got f subscript x is going to equal to, well, I'm going to take the derivative with respect to x, and looking at this, I've got kind of a linear function with power terms. And I'm taking the partial derivative with respect to x, so I'm going to hold y fixed. I'm going to treat y like a constant. I get 3x squared times y plus 2x y squared plus 1 plus, well, 0. Because there's no x, it's just a y squared. We're holding y squared constant, so it's not going to change, because by definition it's a constant. And now if I take the partial derivative with respect to y holding x constant, I get x cubed plus 2x squared y plus 0 plus 2y. Now that we've got our first partial derivatives, our first partials, we can go ahead and start computing the second partials. And we know there's going to be 4 second partials here because we have 2 variables. So let's start with f subscript xx. So we're going to take the derivative of f of x with respect to x. That's this right here. And we're going to hold y constant again, so we're going to get 6xy plus 2y squared. Now let's go ahead with f of x, or I should say f subscript x y. So we're going to take the derivative of this again, f subscript x, but we're going to take the derivative with respect to y, holding x constant. So we're going to get 3x squared plus 4xy and plus 0. Next we can do f yx. So now we're looking here at our f subscript y, our first partial with respect to y. And I want to take the derivative of this with respect to x holding y constant. So I'm going to get 3x squared plus 4xy plus 0. And f subscript yy. I'm going to take the derivative of f subscript y with respect to y holding x constant. So I'm going to have 2x squared plus 2. And there we have it. We've computed all the second derivatives. Remember, when we're working with partial derivatives, allow only one variable to change and hold all else the same. Remember that our partial notation is just notation. You're not actually squaring anything here. This is just a recipe that says or at least part of it says take the derivative twice. It's not a power term. And consequently, the following here are not equivalent. So on the left-hand side, that is squaring the derivative of z with respect to x. On the right-hand side, this is the second derivative of z with respect to x.